In this tutorial we are going to learn to model a complete aircraft and conduct steady-state aerodynamic analysis. We will model this aircraft known as the SMK. Let's begin by creating a new file. And selecting the units. Next, the first step in modeling is creation of the coordinate systems for aerodynamic surfaces. We will start by creating the coordinate systems for the fuselage sections. Let's name this local coordinate system LCS1. Since the fuselage section is modeled in the XZ plane of the body coordinate system, the BCS, we shall rotate LCS1 with respect to BCS accordingly. Now, we can create rest of the fuselage coordinate systems with respect to LCS1, so we don't have to rotate them all. Similarly, we will create the coordinate systems for the wing and tail surfaces. We set the wing position with respect to the BCS. And set its dihedral angle to 1.5 and incidence angle to 2.8. Now, we can make coordinate systems for rest of the wing and tail surfaces. Next step is modeling of the aerodynamic surfaces. The Aerodynamic Surface dialog box in the Model tab allows us to define a vortex lattice panel, otherwise called a surface, in terms of its root and tip chord, leading edge sweep angle, mesh density, and half span length. Let us start by modeling the fuselage sections in local coordinate systems 1 through 5. We'll name the first section F1, and start by defining its root and tip chord lengths. We can either define the sweep angle directly or through offset and local X direction. We can also change the mesh distribution of the surface to be uniform, sine, cosine, or a user-defined. For now, we will leave it as uniform. Clicking Preview will generate the surface, and also make it visible in the tree control. Similarly, we can model rest of the aerodynamic surfaces. Now that one half of the wing is modeled, we can simply copy its sections to the coordinate systems on the other side. To complete the wing, once the aircraft modeling is completed, defining the control surfaces is a very simple task. We start by showing the panel IDs in the View tab, to determine which panels will constitute a control surface. Let's model the starboard aileron first. We go to the Control Surface dialog box in the Model tab. Select the Aerodynamic Surface and define the panels to create the control surface. As an advanced option, we can also control the hinge axis system. Similarly, we can create the port side aileron, rudder, and elevator as well. In order to conduct an aerodynamic analysis, we need to first define the CG location of the aircraft. We can do so by defining a mass model. Although a detailed structural model is required to conduct flight dynamics and aeroelastic analysis, only CG is required for simple aerodynamic analysis. Let's define a single structural node at the CG location and click Update. This mass model is now visible in the tree view, and we can right-click on it to calculate the CG. Next, we need to define the geometric parameters of the aircraft in the Geometric Input dialog. Here we can define the aircraft wing's reference chord, half-span length, and reference area. Now we can proceed to the Analysis tab and open the Single Solution dialog. Here we can define the analysis parameters to conduct a quick aerodynamic analysis. Let's put in the aircraft's speed, angle of attack, altitude, and select the geometric parameters that we created earlier, and solve. we can immediately see the pressure distribution over the entire aircraft. With a CP legend on the right side of the screen. On the left we can see the input parameters in the top column, and results in the bottom column. The results calculated for this analysis are the lift and drag coefficients, calculated in the wind axis, the three force coefficients Cx, Cy, and Cz, calculated in the body axis, and the three moment coefficients for roll, pitch, and yaw moments, denoted by Cl, Cm, and Cn. We can also view the lift force distribution over the wing by selecting the options from the View tab. The analysis is now saved and visible in the solution tree. We will now deflect one of the control surfaces and analyze its effect on the lift distribution. Let us deflect starboard aileron by 20 degrees, and solve. We can now see that lift is increased on one side of the wing. The actual lift force values can also be toggled on.